This video looks at the effect gears have on cruise control laws. Now, first of all, we'll just remind you of the general context. The sequence of videos is looking at simple techniques, okay, we'll emphasize that, simple techniques for problem solving. And that's problems which have open-ended solutions. They do not have a single correct answer. And we've suggested you follow a given procedure. First of all, before you even look at the question in any detail, ask yourself, what is the topic and what do I know about this topic? Then, only after you've done that, look at the information that you've been given. And what you'll find is if you iterate between these two and finding new information from putting those two together, then automatically you're going to move towards a solution or proposal for the original problem. And we'll illustrate that here. Now, what you need to remember is that problem solving, that is applying learning to new problems, things where people don't know the solutions, is a skill that's highly prized by future employers. Now, just a reminder, this problem links to video 4 in this series, so you might want to look at video 4 first. So here's the problem. You're given a cruise control law, which is designed for when the vehicle is in a high gear. And what we want to do is investigate how this cruise control law behaves if the vehicle's accidentally in a lower gear, which can easily happen if you're not concentrating. Okay? Now, what you're going to be given is the nominal car model and the control law are given here. So this is the model if you're in high gear. So you've got G equals 3,500 over 1,000 S plus 80. And the nominal cruise control law is this one given here, 0.05 plus 0.005 over S. And what we showed in video 4 was that if you ignore saturation issues, this law gives pretty good closed-loop dynamics. It's an effective cruise control law. Now, we've got to go through our problem process and say, what do we do first? We want to ask, what do I know? Now, here's the thing. You might or might not know this, but a simplified car model, we know it's a mass damper system, but where you're now going to allow some gearing could be given by something like this. Now, if you look at this model, you'll say, how does this differ from the model I had before? Well, the model you had before was K over MS plus B. And you'll see the key difference is that we've separated M into M1 plus M2. And we've said that if you use a lower gear rather than top gear, then one of these terms basically comes into the equation as an M1 over N squared. And that's relatively simplistic, but it's good enough for us to do some investigations. Now, this model can be derived analogously to the gearing system in the second order modelling series. If you go and look at the second order modelling series, you will find one of the videos towards the end looks at gears. Now, why is this? Okay, in essence, if you're in a lower gear, then you're able to deliver more force, or effectively equivalently more power, to the road, and therefore you're able to get a faster acceleration. And so what that means is the effective M reduces. So what do I know? A simplified car model is given as this, where you're allowing for a gear ratio N compared to top gear. The control law is going to be PI, so we've got Kp plus Ki over S. And the overall closed-loop behaviour is given by the standard formula, something like this. Velocity is GH over 1 plus GH. Now, we should emphasise, so far, all we've done is write down what do I know about cruise control, what do I know about the impact of gears on system behaviour. I haven't really looked at the question at all. So now we go and look at the question. What information have I been given? Well, I was given the nominal model and control law for top gear. So there it is. G is 3,500 over 1,000 S plus 80, and there's my PI control law. And we want to compare the behaviour of this system with what happens when you're in a lower gear, but using the same control law. So what's going to happen is instead of the G above, we're going to use this particular G here. So we're going to write G is 3,500 divided by M1 over N squared times S plus 1,000 minus M1 times S plus 80, because we said pretty much this will represent being in a lower gear. Now, of course, what we don't know is we don't know what M1 is, and we don't know what N is, because we weren't given that in the question. So what we're going to do is investigate some different alternatives, because that's what the problem said. It said investigate the impact of being in a lower gear. So what I've done first of all is I've said let's assume that M1 was 1000, and let's look at values of N between 1 and 2. And I'm going to use MATLAB to overlay the different closed-loop responses you get with these choices. Now, that's important because we're doing an investigation. Actually generating lots of figures gives me insight into what the issues might be. So you'll notice if I was in top gear, that's this blue curve, so that's the nominal response. And then what happens as I go all the way down to N equals 2, you find you get this curve up here, and you'll see it's quite radically different. Okay, so what's the impact of using a lower gear with this cruise control? Well, you get faster initial acceleration. You can see that down here, but actually you settle much slower. But there is also one other really key point. The feedback is still safe. You may not get as good a performance as you would like, but the feedback is still safe. It's not going to cause the car to go into a dangerous mode. Alright, what happens if we try M1 equals 500? Then again, N between 1 and 2. And what you notice here is now the responses are a lot more similar. Even when I go up to N equals 2, which is this one here, if you compare that to the response you got if you were in top gear, the difference is quite small. And I think if you were the driver, you might struggle to notice those differences in practice. So the interesting thing is, if the appropriate value for M1 is about half the original M, then actually using this original cruise control law is good enough. And again, you notice the feedback is still safe. Now, what would you do? Although this video has used some relatively simple modelling assumptions, it does give us useful insights we can use for problem solving. So what did we notice about the given PI cruise control law? If you're in a lower gear than you expected, you get faster initial acceleration, but actually slower settling times. If you're in high gear, you get slower initial acceleration, but faster settling, and a little bit of overshoot because of the tuning. So you might be asking yourself, why not use low gear for initial acceleration and then switch to high gear? And then you'll be saying, well, of course, we all know that, but this is the whole point of doing the investigation, to actually discover these things and then be able to implement them. So let's try that. So what we've done here is we've automated a change of gear halfway through the acceleration mode. So you can see the red curve gives you the behavior you get with a gear change. So somewhere, and we're not going to be too precise, somewhere around here, you've changed, okay, from low to high gear. But you're looking at that and you're saying, but it's not made any better. Yes, I've got a very fast initial acceleration, but look over here, my settling time is really, really poor. Okay? Why is that? Well, there's a need for more careful modelling and understanding the link between the throttle and the velocity. And we also, and this is key, we need a better understanding of the role of the feedback in this process, and the fact that feedback has memory implicit in the integral. And the reason we've got this strange behavior down here where it's really slow to settle is all linked to how the integral works. And because the error up to this point here is relatively small compared to what you would have got if you'd been running the blue curve, it means when you switch over to high gear, the memory you inherit from the integral is a much smaller number than the number you would like to have. And that's why it's then very, very slow to settle. Well, that's one reason anyway. So some conclusions. A simplified model gives a good basic indication of the expected behaviour, and so it's sufficient for crude studies. We've shown that a default cruise control feedback law is robust to some extent. It's safe, even if you're in lower gear. And you can change gear, and the nominal feedback will still give reasonable performance. And that was what we said. Investigate. We said, what do you think? What will happen if you use the same control law in lower gear? But what have we also discovered? Effective feedback design should be somewhat more intelligent, and it should actually take account of the gear selection. So we've shown that if you change gear, the model changes, and really you should be changing the feedback law. And therefore that's telling you, actually, I need to do a more detailed investigation. This investigation was relatively crude, deliberately relatively crude, but it's given me enough information to say I've got to do more detailed studies to understand the scenario and to propose some solutions.